Hey everybody, welcome back. This is my third time recording the video. Both the first two times I did not share screen. Let's see what we come up with this time. So we're doing 12.2 in vector calculus, calculus 3 at College of the Sequoias. It's the fall semester of 2022. Let's just jump right into it. Let's look at the calculus of vectors. So we've done limit of f of x equals L for a regular function. What if we use a vector function like r of t? What does the limit as t approaches a of r of t equal L really mean? Well, if I've got my L vector here and r of t is there, as I do values of a approaching, or values of t that are approaching a, like say a minus 3, a minus 2, a minus 1/2, or this line really close, my vector is approaching both the magnitude and direction of L. It is possible to have a vector that is pointing in the same direction as L, but not the same magnitude. Picture anything on the sine or cosine functions. I could point the vector in the same direction, but different magnitudes go to different points. So it needs to have the same magnitude and same direction. Another way of writing this is the limit as t approaches a of the magnitude of r of t minus L equals 0. Does this look a little bit like delta epsilon proofs if we set the right side equal to epsilon? Kinda. Looks like we could do a delta epsilon proof of this, right? Sounds like fun, right? No, it doesn't sound like fun to me. We're not going to do it. Let's just go on to what we're doing with it, though. RT approaching L, the vector means that the components individually have to approach. So x of t and y of t is z of t of r need to approach those components of L, which means we can pass the limit into it, like we do here. Okay, so we pass the limit into it. If r of t, we take the limit as t approaches a equals r evaluated at a, we say the vector function r of t is continuous at t equals a. And we can scale that up to an interval. Continuity at a point, every point on an interval means the interval is continuous on I. Okay. Let's look at our second page. R is continuous at A if and only if, that's how I write, if and only if, its component functions are continuous A, which means this vector is continuous if each of these are continuous. So let's take a look at it. We can do the limit of it. Let's do it at t goes to 0. Doing the limit of 4t cubed and cosine t is pretty simple for t equals 0. There's more going on with this one, so I'm going to do that one last. I label them R, A, B, and C so we can look at them like that. Limit as t approaches 0 of 4t cubed is just 0. 4t cubed is a cubic polynomial. It's continuous. Cosine t is a sine wave or a sinusoidal wave. It is continuous there. Cosine of t equals 0 is 1. What about here? It equals 1. Why? Well, if we plug in t equals 0, I get e to the 0, which is 1. I get 1 minus 1 on top is 0, and I get 0 on bottom. 0 over 0 is an indeterminate form. We need to use L'Hopital's rule. So L'Hopital is take the derivative of the top and bottom separately, and then evaluate the limit. And if the limit works on this, it works on the original. It's the same limit as the original. So the derivative of the top, we just lose the constant. The derivative of the bottom is 1. When I evaluate e to the t over 1 at t equals 0, I just get 1, so that's B. So I can get the limit as t approaches 0 of r of t. It's 0, 1, 1. Is r of t continuous at t equals 0? The limit exists. This might have been a while for you guys. No, the existence of a limit does not imply continuity. Why? We might have a hole in the graph. So the limit exists as it's coming in from the left. The limit exists as it's coming in from the right. The limit from the left and the right are the same, but we actually have a hole at the graph. T at 0 for y in the denominator means it doesn't work. That'll be it for 12.2a. Peace.